So in this short video, I'm going to go over section 1.1 in our textbook. That's the Mathematical Excursions by Hoffman, Lockwood, Nation, and Clegg. And in section 1.1, the subject is inductive reasoning. I'm going to go through a few of the examples from the book and just add a few little comments to emphasize the point that I think the authors are really trying to make here. So first of all, inductive reasoning is the process of reaching a general conclusion by looking at specific examples. And in example 1, they give you this list of numbers, 3, 6, 9, 12, 15. You ask, what do you think the next number is? Of course, you're going to say 18 because you see that they're fitting a pattern. Each one's 3 larger than the one before. So you think you're just adding 3 each time, and that would make the next number to be 18. That's inductive reasoning. Now, of course, the danger with inductive reasoning is that a finite number of examples like that may fit more than one pattern. So it looks like you're just adding 3, but you might be doing something else instead. Like if I made a graph to illustrate what this, what I'm going to do is put across the x-axis here the position number in the list. Okay, so at position 1 in the list, the number was 3, and then at position 2, the number was 6, and at position 3, the number was 9. And so they appear to be lining up, and that's why you think, oh, okay, I go over 1 and up 3, and that must be the pattern. But the thing is, there's a theorem in algebra, and you don't have to remember much algebra for this class. But the point is, you could find a polynomial curve, a function that goes through all those points, but is not a straight line. If I have 5 points, there's a 5th degree polynomial. By that I mean, let's call this y on the vertical and x over here on the horizontal position. You could come up with a polynomial, y equals ax to the 5th plus bx to the 4th plus cx cubed plus dx squared and so forth, ex plus f, a big old messy polynomial. But if you just pick the numbers right, the a, b, c, d, e, f, you just pick those numbers right, then you can hit the 5 points with this different curve. It's a different pattern. And so in these questions that tell you to predict the next number, in a sense, none of these questions are really fair because there's always more than one pattern that would do the job. And so that's the weakness of inductive reasoning. Even though it's the way science works, it's the way new discoveries are made in math, people notice patterns and then try to find some reason to believe that a particular one of the possible patterns is really what's going on. Okay. So here is in example 2, it's about using inductive reasoning to make a conjecture. And that's once again this idea where you notice a pattern and you make a guess that maybe it's legit, maybe that it will keep going on that way forever. And so it's called a conjecture, which is really just sort of an educated guess. So here's their problem here. They have this procedure. Pick a number, multiply it by 8, add 6, divide by 2, and then subtract 3. You go through the procedure, you get a result. And their question is, well, can that complicated procedure be boiled down to some simpler relationship that's easier to state? Now, you might do algebra to approach that, but that's not what they're doing here. In example 2, what they're doing is they're just going to do the procedure. They just picked a number to start with 5. Okay, that was arbitrary. 5 could have been anything. And then you do 8 times 5 and get 40. And the next step was add 6. 46, divide it by 2, they get 23, subtract 3, they get 20. Okay, so they started with a 5, and they did the procedure, and it gave them 20. Okay, so now what if they started with 6? Let's do some scratch work over here. Okay, I'm going to take my 6 and I multiply by 8. And then I add 6. Get 54. And then I divide by 2. I get 27. And then I subtract 3. I get 24. So 6 turned into 24. And then if I do it with a 10, let's see what happens there. So I do 10 times 8, 80. Add 6, I get 86. Divide by 2, I get 43. Subtract 3, I get 40. So 10 went over to 40. You could do more of these, but look, 5 became 20, 6 became 24, 10 became 40. You could make a guess or a conjecture. That the procedure simplifies so that what you're really doing is you're just multiplying times 4. Okay. So that process of looking at a bunch of examples and guessing the pattern, that is inductive reasoning. Now, in a later example, in example 5, they're asked the same question again, but they want you to use deductive reasoning to solve the problem. Now, deductive reasoning has its own problems, but with that, you start from simpler principles that you believe to be true, things you think you've already established, and then say, well, if those things are true, then some other things must also be true. So our procedure was to take a number and multiply it by 8. So I'm going to let x be the number. And I take my number and I multiply it by 8. And then I take that result, that 8 times x, and I add 6. And after I've divided by 6, after I've added the 6, I take the whole thing and divide it by 2. Okay, or that's, in other words, I multiply it times 1/2. Same thing as dividing it by 2. Okay, and then I subtract 3. Okay. Well, if I believe the distributive property of multiplication has already been established, then I can say, all right, I can multiply the half times both of the things in the parentheses. I have 8x's times a half of 8x's, plus half of 6, minus the 3. Half of 8x is just 4x's. Half of 6 is 3. I said 4 and I wrote 8. I should have written the 4. So I have 4x plus 3, and then I have the minus 3 on the end. And 4x, add 3, and then subtract 3. It boils down to just 4x. So what's the point here? So now we have a proof that the original procedure, which was complicated, is the same as just multiplying by 4, which is simple. It's a proof, but like all proofs, it just pushes all the questions back to an earlier level. It's saying the original procedure is the same as just multiplying by 4 if we believe the distributive property and the order of operations. So always in math, you're pushing back to simpler and simpler starting points. At the root of it all, it's just some axioms about set theory. Or in geometry, there's some axioms about geometry. But eventually you push it down to the things that are just sort of true by definition, or you're just saying, well, we've got to start somewhere. So inductive reasoning has the problem that you can notice a pattern, but it's not the only one that might work. And deductive reasoning has the limitation that eventually you come to some rock bottom starting point where you can still argue about what the right axioms should be. Okay, that's all for this video.